Welcome back to the continuation of our QM2 notes, where we have been talking about factoring polynomials. In the first lesson, we took a look at using the greatest common factor and factoring by grouping. Now we are going to start by factoring quadratic trinomials. So quadratic trinomials is definitely something that you should be familiar with from Algebra 1. Quadratics are any polynomial that are of degree 2. So we can see that in 3a, this x has a highest power of 2. This x has the highest power of 2. They're trinomials because there's 3 terms. So these are what we call quadratic trinomials. And we can write these quadratic trinomials in standard form. So we write them in the form ax squared plus bx plus c, where a, b, and c are all real numbers. And let's add just a little bit of information to this. And a is not equal to 0. So a, b, and c are all going to be real numbers, and a is not equal to 0. This is going to be a quadratic trinomial. So quadratic trinomials, we kind of had a process, a key concept into factoring these. So let's actually just take a look at two binomial multiplications. So let's say we have, x minus 2 times x plus 1. And if we multiply those out, you would end up getting x squared minus x minus 2. So expansion through multiplication is when we go this direction. We multiply, we distribute to get to that quadratic trinomial. To get back, this is what we call factoring, and this is what we're focusing on right now. So we want to be able to factor these. So there's kind of a rule or a pattern that occurs when you factor quadratic trinomials. So if we use this form ax squared plus bx plus c, this is going to equal, so let's go ahead and just write that out. So sorry, ax squared plus bx plus c can be rewritten as, let's say, px plus q times rx plus s. And this is where P and Q are going to be factors of A. So where P times Q is going to equal A. Sorry, not P times Q. Let's make this P times R. P times R is going to equal A. And also where Q and S, Q times S, are factors of C. And in addition, if we do this process of distribution, Q times R and P times S, if you add those two together, it's going to be equal to B. So again, that was PS plus QR have to equal B. And this is the kind of the pattern that we want to work with. Essentially, we're going to follow the process of guess and check as we start to look at factors of A and factors of C until we can develop this Q and R value that's going to give us a factor of B. So let's take a look at an example of how we're going to do that. So the first thing that we want to do, if we can, is to reorder this into standard form. So x squared minus 10, sorry, let's change that to x squared minus 3x minus 10. So we're just rewriting the expression. Now we do want to factor this. This is going to factor into two sets of parentheses. It's a quadratic trinomial. We're going to break it down into two binomials. And we're going to follow this rule that we wrote over here. So the first two things have to be factors of essentially x squared. So we know that x times x is going to give us x squared. The next two numbers have to be factors of negative 10. So to get a negative number, you know you have to add a positive times a negative. That's the only way to get a negative number, is to add a positive times a negative. Now what we need is we need factors of 10, so either 1 and 10 or 2 and 5. And we need them in the right location so that if we were to do distribution, the P times S plus Q times R would equal negative 3 or negative 3x. So My factors of 10 that I'm going to use here are going to be 5 and 2. I'm going to choose x plus 2 and x minus 5. Now the way that I can check this, if I take 2 times x, that's 2x. And I'm doing the little distribution here. I'm checking the inners and the outers. I take 5 times x, negative 5 times x, that's negative 5x. Negative 5x plus 2x is negative 3x. And so this would be the correct factorization here for x squared minus 3x minus 10. So the first the first term in each binomial has to be a factor of the leading coefficient. The second term in each binomial has to be a factor of the constant, and then through the process of distribution, you have to get the middle term. So let's take a look at another example. And again, this is something you've done in Algebra 1, but it's maybe has been a while since we've worked on that. What I'm going to do here first in B is I'm going to try to simplify this equation a little bit. It might make the factoring easier. So what I'm going to do is I'm going to factor out a negative number. You don't have to, but sometimes it's easier to factor when your leading coefficient is positive. So I'm going to factor out a negative, or basically divide everything in that polynomial by -1. Now I'm going to go ahead and break this apart into two binomials. And we know that the first term in each has to be x and x. X times x is the only way to get x squared. Now, my next two terms have to be factors of positive 24. So both numbers either have to be positive or negative to give me a positive through multiplication. If I look at this negative 11x, I know in some process of distribution, I'm going to need a negative 11. So I need both of these numbers to be negative. Two negatives multiply to give me a positive, and eventually will add to give me a negative. So now I look at factors of 24. 1, 24, 2, 12, 3, 8, 6, and 24. Reminder, if you use the calculator, you can go to y equals, type in 24 divided by x, take a look at that table, and it pairs together all those factors. So in this case, I'm going to choose 8 and 11. 8 and 3. The reason I chose 8 and 3 is, again, through distribution, I would have a negative 8x and a negative 3x, and adding those together would match up to give me negative 11x. So my two factors here would be a negative out in front, and then x minus 8 times x minus 3. So the process is to take a look at the factors of the leading coefficient, the factors of the constant, and then arrange those in a process that's going to get you that middle term. Let's go ahead and take a look at another example. Now in B, we see something a little bit different here. We see a 2 as my leading coefficient. We can still factor this. Sorry, this should be C. It may say B on your notes, but this should be C. Let's make that quick change. Let's change this to C, and let's change that to D. Hopefully your notes have it correct. So the process remains. I take a look here at D or C, and I'm looking for a GCF, and there is none. So it's a quadratic trinomial. I'm going to break this apart into two binomials that are being multiplied to one another. Now, the first term in each binomial has to multiply together to give me 2, a 2x squared this time. So I know that's going to be 2x and x. So 2x times x is 2x squared. So my first term in each set is going to be, one is going to be 2x, the other is going to be x. Now, my next two terms have to be factors of positive 18. But somewhere through distribution, they have to add together to give me a negative 15. So I know both of these signs are going to be negative. Now, what are my factors of 18? Well, if I take a look at the calculator, I can go ahead and list these out real quick. 18 divided by x, and there we can see them on the table. 1, 18, 2, 9, 3, 6. So those are my factors of 18. Now, what I have to be careful of is those are the numbers that we're going to use. We have to make sure we put them in the right location and use the right numbers in a way that's going to give us a negative 15x through distribution. So you can do a little bit of a guess and check method here. I'm going to use 2x minus 3 and x minus 6. Now, if I check this through distribution, I get negative 3x and negative 12x. Negative 3x plus negative 12x would give me negative 15x. So this would be the correct factorization. Now let's say I made this incorrect real quick. Let's say I put the 6 here and the 3 there. I used the right factors, but I just put them in the wrong spot. Well, if I check that through distribution, that gives me negative 6x and negative 6x. Negative 6x plus negative 6x does not equal negative 15x. So I do have to check and make sure that through distribution, I'm going to get the correct middle term in order to make sure my factors are correct. So this should factor into 2x minus 3 and x minus 6. If you get this process, go ahead and pause the video and see if you can do D. Let's go ahead and take a look at D. So in D, I'm looking for a GCF. Unfortunately, there's not one. So I'm going to have to work through this with a leading coefficient of 6. So I have some options here. I can go with 6z times z, or I can go with 3z times 2. I'm going to go ahead and try 3z times 2z. 3z times 2z does give me negative 6z squared, so let's hope these work. Now, my factors are going to be factors of a negative 35. So I know that one of my numbers is going to be positive, one of my numbers is going to be negative. I have to make sure I find which numbers and put them in the right spots. So my options are 1 and 35, 5 and 7. So what I can do here is almost a style of guess and check, pick some numbers, put them in a location and make sure that it works correctly. So let's say I use, let's say I use 3z plus 5 and 2z minus 7. Let me check these. So when I look at the distribution, the inners would be 10z, a positive 10z, and the outers would be negative 21z. When I add those together, that does give me negative 11z, so I have the correct factorization here. So my correct factors would be 3z plus 5 times 2z minus 7. Now, if you did not get those factors correct, you do want to make sure you start to move some pieces around. Maybe try a different combination of factors or a different location, maybe different signs in front of your 5 and your 7 to make sure that you get that negative 15 through the process of distribution. So this is how we factor quadratic trinomials. The next thing that we're going to look at is the difference of two perfect squares. So this is actually something that we talked about with imaginary units when multiplying conjugates. So I guess I showed you guys a little bit of a shortcut with multiplying conjugates. And it actually comes from using the difference of two perfect squares. So conjugates, let's say I have a plus b, and I multiply that to a minus b. And then I do the distribution. I would get a squared plus ab minus ab minus b squared. And this would end up being a squared minus b squared. And so this is a shortcut I showed you with conjugates. We did the multiplication, the expansion going this way. Now we're going to use the factoring method going that way. So basically what I can do is if I can find a value that's being squared and that value is being subtracted by another value that's being squared, I can write them into two conjugates. So let's go ahead and take a look at 4a. So in 4a, what's being squared for the first term to give you x squared is just x. What's being squared for the second term to give you 25? That is 5. So if I subtract x squared and 25, that's going to give me conjugates with the terms x and 5. So this is going to be x plus 5 times x minus 5. Now you could go through this process with the idea of factoring a quadratic trinomial, which we just did, with that middle term needing to be 0, but this is a shortcut here. So anytime you have a term that's being squared and it's subtracted by another term that can be squared, we can break that down, factor those into two conjugates. Taking a look at another example. In B, what is being squared to give me v to the fourth? Well, v squared is being squared. What's being squared to give me 1 over 81? Or 1, yes, 1 over 81. Well, 1 squared is just 1, and 9 squared is 81, so 1 over 9 is being squared. So what this breaks down into is 2 conjugates with v squared plus 1 over 9 and v squared minus 1 over 9. Now notice the first set of parentheses is a binomial where we have an addition of 2 terms. So we're not going to do anything there, but take a look at the second binomial. That's a subtraction of 2 terms that are being squared. So v is being squared, and 1/3 is being squared to give me 1/9. So now I can break this down even further. Leading v squared plus 1/9. Now I'm going to have the conjugates of v and 1/3. So v plus 1/3 times v minus 1/3. So this one takes us a little bit two-step process here when we have 2 perfect squares. We have perfect squares to start, then we have perfect squares part of the way through, and we want to use that method to get 2 sets of different conjugates to fully factor out this binomial. If you kind of get the process, see if you can pause it, the video, and do C. Taking a look at C, we're looking for something that's being squared to give me 4w squared. So 2 squared gives me 4, w squared gives me w squared. So 2w is being squared. What squared gives me 81? 9. So now this is going to break down into conjugates of 2w and 9. So 2w plus 9 and 2w minus 9. And these are all examples of perfect squares. So when a plus b is being multiplied to a minus b. Now there are some other shortcuts that we can have that aren't perfect squares but deal with this combination of a plus b. So often when I get a squared minus b squared is people wanted that to come from a minus b squared. But this is not the case because there's that distribution property that goes on when you square a number. So if I take a minus b, and I'll do this down here real quick and then erase it. If I take a minus b times a minus b, I would get a squared minus ab minus another ab plus b squared. So a minus b squared is actually a squared minus 2ab plus b squared. A similar thing would happen if I took a plus b and I squared it. So if I took a plus b and I squared that, I would get something similar. I would get a squared plus 2ab plus b squared. So this may help us simplify some different type of expressions. So let's take a look at 4D. Now, the first thing I may notice in 4D, and we haven't talked about this yet today, but there's a GCF. Each of these terms can be divided by 3m. So I'm going to factor out 3m. And now what I'm left with is 4m squared minus 4m plus 1. So what I may notice here is that if I look at something that's being squared to give me 4m and something that's being squared to give me 1, well, 2m would be squared here, and 2 and 1 would be squared there. And if so, I could write this as 2m squared minus, we'll just leave this as 4m, and then plus 1 squared, which is the same as 2m minus 2 times 2m times 1 plus 1 squared. So this matches that expression. So I can rewrite this as 3m times 2m minus 1 quantity squared. Now, I could have definitely factored this using the concept of a quadratic trinomial, but I'm trying to give you some shortcuts to work around that. So if we know these rules, excellent. If you don't know these rules, you can get to this through the process of factoring quadratic trinomials, which we started this video with. This looks like a pretty good place to stop for this part. So tomorrow, when we reconvene in class, we will take a look at the sum or difference of two perfect cubes. As always, thank you guys for tuning in, and I'll see you soon.